All right, welcome to part 2 of our related rates notes. We're going to start here at example 4. The first 3 examples we did had right triangles in them. This does not. I don't want you to get in the habit of thinking, oh, related rates are all right triangles. That's not true. I just started with that because it makes things a little bit easier. So here's related rates where we have the volume of a sphere and the surface area of a sphere. And if the surface area is changing at a rate of 30 square inches per second at the moment that the radius is 8 inches, what's the rate of change of the volume of the sphere at that moment? So what we're going to do here is actually say, well, they gave me the equations that I need. Let's start writing everything kind of mathematically. So I have V equals 4/3 pi r cubed, and I have S equals 4 pi r squared. And the surface area is changing at a rate of 30 square inches per second. So that really means ds dt is 30 at the moment that the radius is 8. So they're telling me the radius is 8. What is the rate of change of the volume of the sphere at that same instant? Well, I'm using ds dt and dv dt, which tells me I should probably take the derivative of each of these equations with respect to t. So I'm going to take a second and take the derivative of each equation with respect to t. d dt, d dt. You should be doing the same thing while I sing a song about it. d dt, d dt. Okay. The derivative of volume would just be dv dt equals, now the derivative of 4/3 pi r cubed, when I bring the 3 down, it's going to cancel with that 3. So it's going to become 4 pi r squared dr dt. And then over here, I'll have ds dt equals 8 pi r dr dt. All right, so I know I want dv dt, and I have r, but I don't know dr dt. But I also have ds dt, so why don't I substitute these into my second equation, and I'll kind of like make a chain reaction here. So if ds dt is 30, when r is 8, then I can solve for dr dt. Look at that. dr dt is my only unknown. So dr dt is going to be 30 divided by 64 pi. Now I can substitute this into here. So then I have dv dt equals 4 pi r squared. I'm using the same r, so that's 8 squared, times dr dt, which is 30 over 64 pi. Well, isn't that nice? 8 squared is 64, and pi cancels with pi, so I just have 4 times 30, and dv dt is 4 times 30, which is 120. And it says, what is the rate of change of the volume of the sphere at that moment? They don't ask for units, so I don't need to give them, but just so you know, volume is going to be measured in what? Cubic inches per second. I'm trying to get rid of that dash. It's going to be measured in cubic inches per second. Okay? So there's another look at related rates and something that's not a right triangle. All right, so the next page is called Cones Are Special. And the reason I sing-song that and say cones are special, oh my goodness, cones are special, is because cones are special. This showed up on an AP exam a while ago, and all my kids came running back, Mrs. Fibber, cones are special! Because sometimes cones show up because, you know what? They're special. So here's why cones are special. If I have a cone, okay, and I am filling up said cone, with water or sand or whatever it happens to be, the height and the radius have a special relationship. So if I look at my height versus my radius, if I draw in a truncated part of this cone, I have a new h and a new r. But you know what? If I look at these two triangles, this purple one and the dotted line one, don't they both have a right angle? Yes, Mrs. Viver, they do. Don't they both share an angle up at the top? This is the angle of the little triangle and the angle of the big triangle. Yes, Mrs. Viver, they do. And then in geometry, didn't you learn if two triangles have the same angle, there's something called angle-angle similarity? Mrs. Viver, I don't remember that. That's okay, it's true. These two triangles are similar, which means h over r is equal to h1 over r1. And that means that h over r is constant as you fill up a cone. Okay, so let me show you how that works and why it makes them special. So water is being poured into a cone-shaped cup with a height of 6 inches and a diameter of 4 inches. So draw a cone-shaped cup here. I have one already drawn for me because you know what? I'm special, just like a cone. So my diameter is 4 here. I go 4 all the way across. And my height is 6. Okay, if water is flowing in at a rate of 5 cubic inches per second, how fast is the depth of the water in the cup changing at the instant that the depth of the water in the cup is 2? All right, so when I say depth, what I really mean is height, because what's happening here is we're kind of making the cone grow bigger, because right now I have a conical shaped volume of water, and then as I fill up the water, I get bigger conical shaped volumes of water. So this is all really based on the volume of a cone, and the volume of a cone is 1/3 pi r squared h. So if I want to change the volume of a cone with respect to time, I have to take d dt of both sides of this equation, and I end up with dv dt. And on this side, I have a product rule because it's r squared times h, which is a product. So I need the first times the derivative of the second plus the second times the derivative of the first. But that's a lot of unknowns, and I really don't want to deal with all that unknowns. So what I'm going to do is say, you know what? Cones are special. And I'm going to rewrite this. If we look over here, I have 4 for my initial diameter and 6 for my initial height, which really means 2 for my initial radius and 6 for my initial height, which means h over r is always going to have a ratio of 6 to 2, which is 3. So if I want to look at this and I want to rearrange things, I can say, you know what? H was probably the easier way to start this. H equals 3r, which means I can replace all the h's with 3r. Or, since in this I'm interested in dh dt, I really want everything in terms of h, so I can rewrite that as 1/3 h equals r. So basically I had that. I had h equals 3r if I multiply by r, which turns into 1/3 h equals r. The reason I knew to do that is this question says how fast is the depth increasing? Depth is h. I want in terms of h. So where does that lead me? Well, here's what it does. I can rewrite volume as 1/3 pi r, here's my new r, squared h, which really means my volume is pi over 27 pi over 27 h cubed. Well, 1/3 squared is 1/9. 1/9 times a third is 1/27 times pi is pi over 27. H squared times h cubed. And now, when I go to take the derivative of both sides, d dt, I have dv dt equals, well, that would be 3 pi over 27, or pi over 9, h squared dh dt. No product rule needed. Well, I want to know how fast is the depth changing, so I want to find dh dt. When the depth is 2, I have h, and I know dv dt is 5, because the water's flowing in at 5 inches cubed per second. So I have 5 equals pi over 9 h cubed, h being 2, h squared, 2 squared, dh dt. So this is going to be 4 pi over 9, but I want to solve for dh dt. So 4 pi over 9, I'm going to multiply both sides by 9 over 4 pi, which is going to basically make this stuff cancel with that stuff. And I have 45 over 4 pi, whatever that happens to be. If you really want to know what that is, type it into your calculator. My calculations tell me decimal is equal to 3.580. And I truncated, I didn't round. If you rounded, it would be 3.581. And let's say this is height, so that would be inches per second. Okay? All right. Before we get into the next one, I want you to kind of look at it and see what's happening here. And I want you to think about the differences between a cone and a cylinder. So take a second, think about the difference between a cone and a cylinder. I'm going to move that. So coffee is draining from a conical filter into a cylindrical coffee pot at the rate of 10 cubic inches per minute. So this is dripping down here at a rate of 10 cubic inches per minute. How fast is the level in the pot rising? So how fast is that moving up when the coffee in the cone is 5 inches deep? So when that's 5 inches deep, how fast is the level in the cone falling at that moment? So we're interested in two volumes here. We're interested, I don't know what happened there. We're interested in the volume of a cone, which is going to be 1/3 pi r squared h. And we're also interested in the volume of a cylinder, which is pi r squared h. All right. So first things first, I'm going to think about my cone and remember that cones are special. So this cone starts off with a radius of 3 and a height of 6. So I know 3 over 6 equals r over h. So if I want, let's see, r in terms of h, r is going to be 1/2 h. So my volume is 1/3 pi times 1/2 h squared times h, which is going to give me pi over 12 h cubed. All right, and this is definitely changing with time, so if we take the derivative of both sides here, I get dv dt equals pi over 4, because it would be 3/12, pi over 4 h squared dh dt. And let's see, what's dv dt for the cone? Well, the water's dripping out of the cone, so dv dt for the cone is technically negative 10. Pi over 4h is 5. dh dt, that'll tell me how fast this water level is dropping. So if I take a peek at this guy, I'm going to have dh dt. Let's see, I'd have to multiply both sides by 4 over 25 pi times 4 over 25 pi, which is going to be negative 40 over 25 pi, which again, if you really want a decimal for this guy, is going to be, where am I? Negative 0.509 on that one. Now I need to come over here and talk about the cylinder. Well, cylinders are kind of special too, because when we think about the cylinder, as the water drips into the cylinder, and I think about the rates of change of the radius and the height, is the radius of the cylinder dropping or increasing or doing anything? No. The radius of the cylinder is constant, because basically we're thinking that every time water drips down and goes doop, doop, doop in the bottom, every time that happens, we're basically thinking that the water splashes and spreads out to fill the whole bottom of the cylinder all at once. So we could rewrite this as V equals pi times 3 squared times h. So the volume of my cylinder is 9 pi h. And now if I take the derivative of that, d dt, I have dv dt equals 9 pi dh dt. And let's see, the volume of the cylinder is changing at the rate at which the coffee's pouring in. So that would be 10 equals 9 pi dh dt. So dh dt is going to be 10 over 9 pi, which again, if you want that as a decimal, is 0.353. And that is that. So the last couple examples we talked about related rates as they pertain to volume. And basically, this is kind of how it all happens. So we are going to work on the last page at a separate time, so you are done for now. Enjoy the rest of your day, evening, morning, whatever time it happens to be while you're watching this. Toodles.